for 35 minutes and plus 10 minutes for questions. It will be recorded and posted on YouTube. Welcome, Peter.
Thank you, Amina. Yeah, it's wonderful to be here and a pleasure to be able to talk to all of you about the work that we're doing. Let me go ahead and share screen here. Okay. Great. This is joint work with Shane Henderson, who's on the call, and David Schmoys, another faculty member at Cornell, and then a number of PhD students, as well as Brian Liu, who's a former undergraduate at Cornell. Just to situate things, I am a faculty member at Cornell University, which is in Ithaca, New York, which is about 4 hours drive from New York City in the state of New York in the United States. What I want to do is just tell you about the strategy that we had for bringing students back to the university in the fall of 2020, the thinking that went into that, especially from the point of view of data science, operations research, mathematical modeling, and then talk to talk through all of that and to use that as an example, both for people who are interested in COVID-19, and then also as an example of how we can use math to support decision making. So the strategy that we pursued in 2020, in the fall of 2020, in the spring of 2021, at a time when many other universities were closed, was to bring back most of our student population, to offer in-person classes, not to all students, but to many students. So about 80% of students had at least one in-person class. We did arrival testing for SARS-CoV-2. We also did aggressive asymptomatic screening. So we tested all undergraduates twice a week, most other people once a week in the university population. And then in the spring, we pivoted over to testing people in what were observed to be higher transmission populations more frequently. We also developed something that's called adaptive testing, where we expand the traditional circle of contact, the traditional approach to contact tracing, where you test only close contacts. We expanded that to something where if, let's say, a member of the men's squash team tests positive, even if the other members of the squash team are not enumerated as close contacts by the positive person, we would go ahead and test them. All of this testing was enabled by something that's called pooling that I'll talk about, and then a large ability to run PCR, the chemical reaction used to test, one of the chemical reactions used to test for SARS-CoV-2 that was available in our veterinary school. We had restrictions on social gatherings, masking was required, travel outside the community was strongly discouraged, and then these lectures that we had were socially distanced. So that was our strategy. And to jump to part of the punchline, it worked in 2020, and we had a relatively small number of cases given the size of our population. And then more recently, over the summer of this year, as vaccination was becoming more available, we had a fairly different strategy. So essentially almost all students returned for in-person instruction. We required vaccination. We continued with some of the testing, but at a relaxed pace. And we had removed much of the capacity from our lab. And so we tested unvaccinated students and employees twice a week, of which there weren't that many, and then tested some vaccinated undergrads and professional students once a week. And then students in fraternities and sororities, actually, we elevated to twice a week this past weekend. Masking is required, and then we only had light limits on social gatherings and had in-person lectures. So a much more, not a fully normal semester, but much more normal than the year before. And so we're in the midst of observing what that's like. So starting about a week and a half ago, on August 24th, we saw a relatively large cluster in this population. So what I want to do is kind of, given this context, talk about how we arrived to these strategies through the use of mathematical modeling, and then what worked and what didn't work, and what we can learn from it. So to back up, in June of last year, 2020, we were looking at cases. These are, this is the number of confirmed COVID cases in the United States reported each day, starting around the beginning of the pandemic, going through when we were starting, when we needed to make this decision. So the question we needed to answer was, should we ask the students to return for in-person instruction next semester? And the thing that was on the minds of many individuals is that, when you invite students to come to university, they have parties, and some of the parties that they have look like this, and these are not especially safe when there's a pandemic. At the same time, so that basically fear about transmission was pushing in one direction. Another concern that people in the community had was that it's a college town where a number of people depend on the students for their livelihood. Both people associated with Cornell University, which is located in the town, and Ithaca College, which is also in Ithaca, New York. Those people depend on the students for their livelihood. Also, local businesses depend on students for their livelihood. So, that was one thing pushing in the other direction. Also, a concern for the learning outcomes of our students, which tend to be worse when students are engaged only in virtual instruction, and then also mental health outcomes associated with having our students be isolated away from each other and only able to come into contact with each other virtually. So, those things are pushing us towards wanting to have students around. This was during a period when a number of basic supplies were just not all that available in the United States and in many places around the world. In particular, here's an article from the New York Times that talks about how months into the pandemic, supplies for being able to run tests for SARS-CoV-2 were not available. At the same time, we were really lucky in that Cornell has a really large school for veterinary medicine. And part of the mission for that, for CVM, College of Veterinary Medicine, is to be able to supply viral testing to nearby dairy farmers to help prevent viral outbreaks in dairy cows. And as a result of that mission, they have a large capacity for running polymerase chain reaction, PCR, the test that we use to test for SARS-CoV-2, on site. And so what we realized was that we'd be able to take that capacity developed for cows and for other animals, and after satisfying some regulatory requirements, to be able to apply that to humans, and then also to dramatically expand how much testing we could do through something that's called pooled testing, where you collect samples from 5 individuals. So, you swab their nose, and then you put each of those swabs into some fluid. And so you have 5 test tubes with fluid, and then you use a pipette and you pipette out of each of those tubes some fluid and put them into a common vessel, and then run a single chemical reaction to test for the presence of virus in that vessel. And if it comes up negative, then that's an indication that none of those 5 people have virus, and only when it tests positive, which doesn't happen that often, do you then run individual tests for those 5 individuals. So that's a way to dramatically scale up your capacity for doing testing, and gave us the thought that maybe we could test everybody on campus. And not only could we test everybody, like they did here in Wuhan, where they tested 9 million people over 10 days, not only could we test everybody, but we could test everybody repeatedly. So the strategy that we thought about was, we test all students on arrival, we test all students every X days, where our job was to come up with the X. Then we also do contact tracing, and we isolate positives in a local hotel, do this adaptive testing that I talked about, and then mask plus social distancing. And the question from the administration to us, a bunch of mathematical modeling people, was, will this work? Can we safely bring back students and use this strategy to prevent an outbreak from causing lots of negative health outcomes? So, as mathematical modeling operations research people, we sat down and we built a model. We actually built a couple of different models. Here's one of the main ones that we built. So it's a stochastic compartmental simulation, and it keeps track of the number of people in each of several different compartments on each day. So the compartments that we think about are, first of all, broken out by disease state. So whether a person is susceptible to the disease but has no exposure, is exposed and has the virus growing inside of them, but it's still early, so they're not really able to infect others yet, or it's later and they've become infectious, but they're not yet symptomatic, or it's even later and they've either developed severe symptoms, the kind that would send you to the hospital, or mild or mild symptoms, or they don't develop any symptoms, and they're not going to in the future. So we track those quantities. Oh, and then once you recover from the disease, then you have some degree of immunity. And then we additionally track whether someone is free and kind of in the general population, or has been detected either through a positive test or through contact tracing, and then is in quarantine or isolation. We also sometimes quarantine people that have not been infected, and so you might have a susceptible person who's in quarantine. And then we have non-exponentially distributed times in each of these states, and so we need to actually track we break these compartments up into smaller compartments which track how many people have been exposed for 1 day, how many people have been exposed for 2 days, et cetera. And when you run these kinds of simulations, you get trajectories that look like this. So here I'm showing the total number of active cases here in the purple line, and the active cases are broken up into people that are in the general population. So those are the green, indicated by the green line. So on the x-axis is days in the semester, and on the y-axis is number of active infections. And you see that in this particular simulation, where I'm applying a contact tracing and testing intervention in order to control prevalence that's introduced at the start of the semester from arriving students, you see that active cases are rising, but the free and infectious population is dropping as I find positives and contain them. Then as people progress through their disease, the number of recovered people is rising, and the cumulative number of people who've been infected with COVID rises initially and then levels off. So we built that kind of fairly detailed stochastic model for understanding disease propagation in the university population. And then we also built differential equation models that are simple enough so that you can write them down on a pencil and paper, and you can do calculations with them that you can either put into an Excel spreadsheet and work with really quickly, or even do calculations in your head in order to understand whether a particular set of parameters or a particular set of interventions are going to result in an outbreak or not. So the simplest one, which is probably one a number of people, if you've been working in this area for a little while, are familiar with, is an SIR model. So this has 3 compartments. There's a fraction of the population that's susceptible. there's a fraction of the population that's infectious. And then at a rate of beta, each infectious person comes into contact with other people in the population. And the fraction of those people that are susceptible is just given by the current value of ST. And so that results in a flow from the susceptible compartment into the infectious compartment. At the same time, people who are infectious, they recover at a rate of gamma. So I get a flow of gamma times I into the recovered compartment. And we get these, these equations for the derivatives in my differential equation. I pulled this from Wikipedia. These are some trajectories from this particular standard epidemiological model. And you see that the trajectories that you get from this are fairly similar to the ones that we get from our more detailed stochastic compartmental simulation. So it's fairly representative and gives a kind of a quick kind of rough sense for what's going on. And the nice thing about this differential equation model is that it tells you a really simple answer for when an epidemic happens. You can work with the set of differential equations, and you can note that the rate of growth for the infectious population is just this contact rate parameter beta times I times S minus the rate at which people recover. And then when most of the population is susceptible, which is the condition that we want to be in, that we're engineering our interventions to be able to achieve, we see that this rate of growth for the infectious population is just the difference between beta and gamma times I. So if beta minus gamma is positive, strictly positive, then you're going to get exponential growth, at least for a little while, until the susceptible population becomes small enough that this derivative becomes negative again. And a different kind of equivalent way to write that down is that if you define R naught to be the number of additional people that each infectious person infects, which in this model, given that an infectious period lasts 1 over gamma days, and you're infecting people at a rate of beta, that number of additional infections is just beta over gamma. And you see that this kind of condition inside the differential equation that determines whether you get exponential growth or not is just whether R naught beta over gamma is strictly greater than 1. So, we can use that in order to quickly understand whether our code is correct, and also to, to be able to answer kind of questions on the fly in a meeting about, whether something is safe or not. So using this pair of models, we tackled the question of, would it be safe to bring back the students if we did regular surveillance? So here's some simulation results where I'm showing a histogram, and I'm showing across simulation trajectories what fraction of the population on our campus is infected over the course of a single semester. And what we found was that if you don't do surveillance testing with reasonable estimates for model parameters at the time, you get more than half of the population being infected across, the large majority of simulation runs. Whereas if you're testing everybody once every 5 days, then the fraction of the population, is typically substantially smaller, maybe less than 5%. You can understand this as well using a variant of the SIR model, where in addition to having people leave the infectious compartment because they recover, you also have people leave because they're being tested. So if I test a fraction T on each day, and I assume an instantaneous result from my test, then the rate at which people leave is, changes from gamma times I to gamma plus T times I. And then if you repeat the same calculation that I gave you, that I walked through before, you find that the epidemic grows if effective R naught, which is the number of secondary infections a single person has in the presence of an intervention, we find that the epidemic grows if that effective R naught is strictly greater than 1, and it's given by beta over gamma plus t. So when you plug in plausible numbers associated with an unvaccinated population using the viral strains that were dominant in 2020 that had an R naught of about 2.5 and an infectious period of about 10 days, then what you see is that in order to keep the epidemic from growing, you need to screen without behavioral interventions that would reduce R naught. You need to screen at least 15% of the population per day. So that's screening everybody about once per week. And so that kind of thinking, the simulation results, and then this kind of differential equation modeling gave us hope that this kind of intervention could work if we could do something like testing everybody once every 5 days or once a week. We also understood that if you target your testing so that you test if you have a more detailed model where you have different subpopulations, some of which come in contact with other people more frequently than others, then so if you have this situation which is realistic, that different subpopulations have different rates of contact, we found that if you test those more social subpopulations more frequently, there's a huge amount of benefit in doing that, and you can get much greater epidemic control. So here's like a Pareto plot where we look at different testing policies. So you break your population up into groups. For example, undergraduates associated with fraternities and sororities, other undergraduates, MBA students, PhD students. So you break up your population into different groups, and if you can do a reasonable job of estimating how much social contact each of those groups have, then so we have different testing policies that test those groups at different rates, and each one of these dots corresponds to such a testing policy. And then we're plotting the number of tests that we need to be able to do in our lab per day and the total number of infections that we're expecting in the population over the course of the semester. And then we can trace out this Pareto frontier, and this is how we selected the different rates at which we would test different groups over the fall semester. And then you can also understand this with a differential equation model. You basically get, you construct a differential equation model where instead of having a single susceptible compartment, you have a susceptible compartment for each group. The same thing for infectious compartment. And then people in an infectious compartment associated with, for example, undergrads in low density housing, they both infect other susceptible undergrads in low density housing and susceptible undergrads in high density housing. And so you get this differential equation that governs the dynamics of this system. And what you find is that in order to prevent an epidemic, you need all eigenvalues of this particular matrix to be negative. And in the special case where beta is diagonal, which is actually, we find fairly representative of reality, it just decomposes to simply that, beta I needs to be strictly less than the sum of the rate of recovery and the rate of testing for each population. So that kind of shows you that indeed those groups that have larger beta I's, since everybody has the same gamma I, those groups that have higher rates of social contact, bigger beta I, they need to have higher testing rates in order to make sure that we don't get an exponential growth. So, that gave us hope, but at the same time, we were really concerned about uncertainty. We didn't really know the rates of contact for the different subpopulations. And if you graph, if you fix a testing policy and then you increase the rate at which people come into contact with each other, what you find is that the percent of the population infected rises really rapidly. So it stays kind of reasonably flat for a while, and then it reaches an inflection point where you go from, 1% of the population being infected to more than 10% of the population relatively quickly. And so we were really worried that our estimates were wrong and that we were going to get an exponential growth despite our best efforts. So we did a huge amount of sensitivity analysis, things like this, where we graph the rate at which people are coming into contact with each other on the x-axis, some measure of kind of an important parameter that we didn't know. And then on the y-axis, we graph the strength of our intervention, in this case, the rate at which people could test. And there's two regions in this graph. There's kind of this region in the top left, where the number of infections in the population is relatively small, where your intervention is stronger than this nasty parameter. And then there's the region in the lower right, where the opposite is true, and you get 8,000 infections in the population of 16,000 people or more. So then, basically it came down to how far up on the y-axis do we think that we can go if we really need to, and how confident are we that the parameter that governs reality, the frequency with which our undergraduates come into contact with each other, how confident are we that that parameter lies in far enough to the left that our intervention will be strong enough? We were fairly confident, but not 100% confident. Let me skip this in the interest of time. So that was the question, right? Should we bring the students back? Do we think that we can test enough to make it work? We then thought about the counterfactual. So what happens if we don't bring our students back? We would then have students who would be engaged in taking classes online. We did a survey of the students that suggested that at least several thousand of them would, instead of spending the semester in their parents' basement, not a great place to spend your semester, they would come back to Ithaca, a lovely place in the fall, and take classes online there. Talking to local landlords, there were a significant number of people who had signed leases with them, and that corroborated our belief that several thousand students would come back for instruction to the town. Moreover, if we had people that were doing virtual instruction, it would have been hard for us to mandate screening for them because there would be no physical connection with them. From a legal point of view, our ability to mandate and then enforce compliance with screening would have been difficult. And under many realistic parameter regimes, what we found was that the number of infections under this virtual instruction scenario with, let's say, 3,000 students in Ithaca would be worse than with the full student body, but better compliance with testing. Here I'm showing a graph demonstrating that, where on the x-axis, I have the number of predicted residential infections in the Cornell population between 100 and 10,000. And on the y-axis, I have the same thing when we move instruction to virtual instruction. And then each point represents drawing a set of parameters for our simulation from a Bayesian prior distribution over parameters, and then running the simulation for both scenarios. And what we see is that in almost all scenarios, the number of infections under virtual instruction is larger than under residential instruction, and often is much larger. The small number of parameter settings in which that's not true tend to have both virtual instruction and residential instruction result in a relatively small number of infections. And so based on that, we made the case to the administration that it would be safer for the university community and also the local community if we went ahead and offered residential instruction. Here's an example of another university, Michigan State University, that went the opposite direction, that chose to go ahead and move classes online, had exactly that scenario happen where a number of students came back to the town and engaged in remote learning locally. And there was an outbreak. For example, there were 640 cases in the week of September 7th in East Lansing, Michigan, where Michigan State is located. All right. So the strategy was effective in 2020. And the number of cases that we had during the 2021 school year, so from mid-August 2020 until June 2021, was comparable, actually, about 1,000 infections was comparable to schools that didn't open, that didn't have their students return. About 1,000 infections. Now, here we are at September 7th, and we're currently dealing with this. So what I'm graphing is time on the x-axis. This is the start of our fall semester. And this is the number of confirmed infections. Blue is students, gray is employees. So what happened was that we mandated vaccination for students, and pretty much all students are vaccinated. Most staff are vaccinated too, and faculty. And it seems that the frequency of testing that we used wasn't quite fast enough. Also, there was a delay, roughly a 2-day delay actually, between sampling and isolating a positive due to a variety of factors. And then also the compliance with testing wasn't particularly good. So as a result of this, we had transmission between pairs of vaccinated individuals, especially at off-campus social gatherings, and then also associated with cohabitation. Fortunately, the vast majority of students who are infected either have no symptoms at all or have very mild symptoms. There are students who have, there are some students who have a fever, kind of flu-like symptoms, but we haven't had any serious illness, at least that I'm aware of right now. We've had about 400 cases in the last 2 weeks. Now, in response to that, we understood these issues and made some changes in order to address it. So we elevated students in fraternities and sororities as twice-a-week testing, made a change that significantly shortens the time from taking a sample to isolating a positive. And then there are new enforcement measures in place in order to improve compliance with testing. And as a result, since the spike, I think this is August 27th or 28th, when we had more than 50 cases, has fallen significantly. So just in conclusion, asymptomatic screening enabled by pooled testing is a super powerful tool for preventing the spread of infectious disease, especially in groups of people that have high rates of social contact. A couple of things that were important for our success in modeling. So one was having mental models for our computer models so that we could move faster and also double check our work and build intuition. Building in on robustness to uncertainty is really important in epidemic models where the response is highly nonlinear, is exponential. And then, I didn't really talk about it, but clear communication with stakeholders and the public. And then the last thing that I'll say is that at least our data shows or very strongly suggests that transmission between two fully vaccinated individuals is strong enough to create exponential growth at least in highly social populations. And that may be something that, that you folks or, other folks who are watching this may want to take away when they think about their own pandemic mitigation strategies for whatever populations that they are in charge of protecting. So let me stop there and see if folks have questions.
Maybe I will start with a question.
Sure.
Oh, thanks for the great talk. So in one of your plots, you had the number of infection versus when you were considering optimistic or pessimistic views to the parameters. Can you bring up that plot again?
Yes.
I was wondering what parameter essentially dominates that behavior.
Yeah,
Because
that's an important question. Let's see. This one?
yeah, this one.
Yeah.
Because because if you increase the if the mixing parameter increases, like the number of infected individuals approach,
Yeah.
like it gets a similar behavior. So what was I was wondering which parameter can affect to separate these curves when the mixing is high.
Yeah. So we have there's quite a few parameters in our model. And the most important one is the one that I'm varying along the x-axis here, so average number of contacts per day. But there are a number of other important parameters. I'm trying to think.
The optimistic, you mean what like the number of tests or vaccination can go from green to orange, say?
So what we have maybe 15 parameters, and what we did is for each one of those parameters, we identified kind of our best guess. So that's the nominal value for that parameter, a pessimistic estimate, and then an optimistic estimate. And then the blue here is plugging in the best guess for each of the parameters. The pessimistic is plugging in the pessimistic estimate for each parameter. So examples of parameters include how effective is contact tracing. So that's for each positive that we find through symptomatic self-reporting or through testing, how many other positives do we find and isolate because of through contact tracing. There's a bunch of parameters associated with the biology of disease progression. So, how long does it take to go from being exposed until you start infecting other people?
And does it include the vaccinated people as well?
So this is work that we did in our summer of last year. So at that point, there were no vaccines.
Yeah, sure.
So no one is, I don't have plots in this deck, but yeah, right now, in order to support the decision-making around our current interventions, we do include vaccinations are super important. And like key parameters there are how effective is the vaccine against infection? How like if you and I are exposed to the same amount of virus and you're vaccinated and I am not, how much more likely am I to become infected? That's really important parameter that's been floating around in the literature by an unfortunate amount. How much does vaccination reduce your ability to infect other people? So those are, and also, what fraction of your population is vaccinated? Those three parameters are really critical for doing modeling estimates for now.
Yeah. All right.
Well, like another key parameter that is really important for differentiating these is how infectious is the virus? Like if you and I are
the different variant.
Yeah.
Yeah.
Other questions? I see there were a bunch of things in the chat.
There are a bunch of questions on the chat, and Shane has been answering almost all of them. And there's just one last question. Yanis has asked, can you talk about hospitalization in unvaccinated and vaccinated populations?
Definitely, super important. And let me do that in the context of this graph. Vaccination does really protect against severe illness. I'm fortunate to not really know that much about hospitalization. Our population of people, so I'll say that yeah, like our population of people, we didn't have that many cases last year, first of all. And then our population, the population that has the highest prevalence is our undergraduate population. And they are young and they're also very healthy, like even compared to other young people around the world. These are very healthy young people by and large. So, you know, we've been really lucky to not have a lot of direct experience. And if you were to get my data, there's not really much you wouldn't really be able to estimate a whole lot about hospitalization risk other than that it's low, based on my data. Now, this spike, I mean, it's, you know, for us, it's a lot of infections, 400 infections, and, you know, no one's in the hospital, at least that I've been told about. And, you know, they're healthy. And so again, there's like directly from the data, there's not a lot that I can say. At the same time, you know, the numbers that you see reported in the literature from various clinical trials do suggest that, you know, vaccination really confers an enormous amount of, so like if vaccination confers, let's say 80% protection against being infected, and then confers, let's say 98% protection against hospitalization, then I think when you work out the math, it's roughly a 10-fold reduction in the risk of hospitalization given that you're infected. So essentially what you can do is you can take, if you want to compare hospitalization risk between this spike and this spike, you know, you can cut it down by a factor of 10, and those, like from a public health, from a health outcomes perspective, at least if the infections stay controlled within the same subpopulation, then that's a way to compare these two very different kinds of infections. Now, some people say that because the risk of severe disease is reduced so significantly by vaccination, that we really shouldn't worry at all about this spike. And I don't agree with that, because we've done a lot of, you know, the fact that this blue line is lower than the peak is because a bunch of people worked a 100-hour week, you know, between August 28th and whatever 1 week from that was. And if we hadn't done that, I think that this line would have kept going up. And when you have 10,000 infections and maybe 1 in 1,000 people needs hospitalization, that is a problem. So I think that the fact that vaccination protects against hospitalization is really a wonderful thing. But at the same time, we do need to be really cautious in high social contact cohorts, even if they are fully vaccinated, because if you let it get out of control, then at least our data suggests that can be a problem from a health outcomes perspective. And better safe than sorry, you know?
Maybe, could I add a little bit to Peter's?
Yeah, please.
Yeah.
Yep.
One thing Peter told us, I think, Peter, you pointed this out, was that there's also the danger of the spillover infections into the family of faculty and into the community itself, where the vaccination rates are much lower.
Absolutely. Our staff, you know, there's much of our staff has high vaccination rates, but there are some cohorts of staff that, you know, maybe have lower vaccination rates. And yeah, I'd hate to have, yeah, and you know, that also creates risks. So that's another reason why why we work hard to prevent, why we work hard to bring this line down.
All right. Just one quick request from Yanis. Would you be sharing your slides? Like, would it be like email personally to you, or?
I'm happy to share my slides, and
Yeah.
I can definitely share them over email, and I just put them in, I think that's accessible. I just put the link in the Zoom chat.
Yep.
Oh, maybe that's not, but here, let me change it so folks can see it. Okay, try that link, and then I'll also send it through email.
Yep. Yep, Yoni wants another question.
Dealing squeeze in one last one perhaps. So Peter, thanks for this. It's actually very exciting how as mathematics faculty member you and your team's work has influenced university policy. Can you position that in terms of the uniqueness or non-uniqueness of this situation? So you've got this university in a rather small town, 30,000 people. How general would this be, and the interaction with the town? When would it work, when not, etc.
Yeah. So I think I should have given a sense of scale. So there's 16,000 undergraduates, a little bit more than 20,000 students altogether, 10,000 employees, and then we're in a county where there's kind of one large metro area with about 100,000 people. So like one thing that's special about this situation is that it was and still is an emergency. And I think that emergencies create opportunities for, changes to the way that things are done. A bunch of people are willing to try new things that ordinarily would have want to do a bunch of process and talk about it for a long time. I think that we were in the right place at the right time. We were a bunch of people that, wanted to help. We had skill sets that were complementary to what needed to be done, both from a mathematics point of view, and then also from the point of view of being people that work with, kind of have. Shane and David and I all have experience working with companies and working with decision makers in a way that it makes sense for them, and that communicating in a way that is compatible with how decision makers need to move and think, and the speed at which they need to do that. So that I think was important. And I also think that we were really helped by the fact that the president of our university, she's a computer scientist. The provost for our university is a molecular biologist. So they're both very technical. They're both scientists, and they're used to making decisions based on evidence. And then they had these really challenging questions they needed to answer, and then they had somebody that wanted to provide evidence in a fast format to them to support that, and they found that palatable. I think those conditions are all necessary, and then the other stuff I think can fall into place. I don't know if you have any other thoughts, Shane.
I guess I would just add that one of the things that I think Yoni might be curious about is the physical situation of Ithaca. And I think, like you painted, I think that the strategy of pooled testing, regular asymptomatic screening, I think it can work just about anywhere. It's harder in a place where you've got more outside infection going on, but it can work. I mean, that was your thesis. You started thinking about that for the international, for the national scene.
I do think that if we were, I think that if we were in a different environment, we would have made, I'm sure that the recommendations that we would have made would have been different, and the solutions we came up with, I think, would have been different. But I do think that if you had those conditions that I described, then a bunch of people that had good math skills and wanted to help, and and were willing to work with decision makers on their terms, I think that such a team can really have an impact.
All right, let's conclude the session, and thank you so much for the great talk. It's really wonderful to have you. Okay.
You're a great audience, and thanks to Shane for helping.
Shane has been answering most of questions. Thanks, Peter.
Thank you.
Thanks,
Shane. Everybody.
Maybe one last thought. You can see that why Peter's such a great communicator and has had such impact at Cornell.
Yep.
Thank you.
Thank you.
Thank you.